Setup and Tele-Operation. Configuring the hardware and software setup for an autonomous car is a critical step in the development process. This lesson covers the practical aspects of setting up sensors, actuators, and communication interfaces. Additionally, it introduces Tele-Operation, allowing manual control for testing and validation purposes. Setting up a robotic system involves careful hardware and software configuration. Tele-Operation serves as a valuable tool for initial testing and validation, requiring a well-designed control interface and safety measures. Real-time feedback, user training, and robust communication protocols are crucial for successful Tele-Operation. Consideration of redundancy and fail-safes, along with remote debugging capabilities, contributes to a reliable and secure teleoperated robotic system. Hardware and software setup. Sensor configuration. Properly mount and configure sensors, such as LiDAR, cameras, and IMUs, ensuring optimal data acquisition. Calibration of sensors is essential for accurate perception. Actuator setup. Configure and calibrate actuators, such as motors and servos, to ensure accurate and responsive control. Verify the correct functioning of all hardware components. Communication interfaces. Establish reliable communication interfaces between sensors, actuators, and the central processing unit. Utilize standardized protocols, such as ROS topics, to facilitate seamless interaction. Power management. Implement robust power management to ensure a stable and uninterrupted power supply for all components. Address power consumption and distribution considerations. Tele-Operation involves controlling a robotic system remotely, typically for testing or initial validation. The operator sends commands from a remote location to control the robot's movements. Control interface. Design an intuitive and user-friendly control interface for Tele-Operation. This interface can include joysticks, keyboards, or custom GUIs based on the application. ROS Tele-Operation nodes. Use ROS Tele-Operation nodes to translate user commands into control signals for the robot. Implement safety features such as emergency stops to ensure operator control. Safety protocols. Establish safety protocols to prevent collisions or hazardous situations during Tele-Operation. Incorporate features like obstacle detection and collision avoidance. Example: the code snippet uses ROS, Robot Operating System, to create a node for Tele-Operation. It initializes a ROS node named teleop_node using rospi.init_node. A subscriber listens to the teleop_cmd topic, which publishes messages of type twist. The function teleop_callback processes these incoming messages, presumably user control commands, to issue robot movement or control commands. The rospi.spin function keeps the program running, waiting for messages until the node is shut down. Real-time feedback. Camera feeds. Integrate camera feeds into the Tele-Operation interface for real-time visual feedback. Enhances operator situational awareness. Sensor data display. Display relevant sensor data, such as LiDAR scans or IMU readings, to aid the operator in decision-making. Challenges and considerations. Latency. Minimize communication latency to ensure real-time responsiveness during Tele-Operation. Optimize data transmission and processing speeds. User training. Provide adequate training for operators to familiarize them with the Tele-Operation interface and ensure safe and effective control. Redundancy and fail-safes. Implement redundant systems and fail-safe mechanisms to handle communication disruptions or system failures. Remote debugging and diagnostics. ROS logging and visualization. Utilize ROS logging mechanisms to record system status and potential issues. Implement visualization tools for remote debugging and diagnostics. Telemetry data. Transmit telemetry data back to the operator, including battery status, system health, and error logs.